In this section, we will talk about properties of functions. A function f is even if for every number x in its domain, the number negative x is also in the domain. The reason this has to be true is if negative x is not in the domain, that means the graph doesn't exist for that point negative x. Okay, so x has to exist in the domain, negative x has to be in the domain, and f of negative x has to equal to f of positive x. Here's what it means. Remember the parentheses contains the input or the x value. So let's say that a particular x value has this output. Then what we're saying is that the negative of that same input also has the exact same output. See? The positive x value and the negative x value have the same output. Here's another example. The positive x value and the negative x value, they both have the exact same output. That constitutes an even function. And notice what happens. So every time we have a positive x and a negative x, you have the same output. So what's happening is on both sides, this is the y-axis, on both sides of the y-axis, we have symmetry, which means that the points are the same on both sides of the y-axis. So the theorem says that a function is even if and only if it is symmetric with respect to the y-axis. So this is an example of an even function. Because if you look at the y-axis, every point as you go to a positive x and negative x is the same, which means that the y-axis creates a mirror image of the function on both sides of it. Okay, so this is an example of a graph that's symmetric, which means it's the same on both sides with respect to the y-axis. This function is not even, because if you look at the y-axis on both sides, the graph clearly is not the same. So this is an example of a function that is not even. We will be determining algebraically whether the function f of x equals 2x squared plus 3 is an even function. Graphically, we have to check for symmetry with respect to the y-axis. Algebraically, we have to use this definition. A function is even only if f of negative x is equal to f of x. So we want to test, does f of negative x in fact equal to f of x? So we need two things for that. We need to know what is f of x. Well, we know what f of x is. F of x is 2x squared plus 3. That takes care of f of x. We have to now calculate what is f of negative x. Okay, we want to calculate f of negative x. For that, remember that the parentheses contains the input, and the input replaces the x in the expression to the right. So instead of saying 2x squared plus 3, remember this x gets replaced with whatever the input is. So we have 2 times our input, which is negative x squared plus 3. Okay, so f of negative x, if you simplify this, negative x to the second power is negative x times negative x. Negative times a negative is a positive. So that's going to be an x squared, and then we have plus 3. So f of negative x is equal to 2x squared plus 3. Since f of negative x equals to f of x, that means the function is an even function. And if you were to graph this online, there's a really good website which we're going to be using later on called desmos.com. So you can go to desmos.com or a graphing calculator, any website where you can graph this. There are a million of those. Here's what the graph would kind of look like. It would kind of look like this. And the reason this function is even is because on both sides of the y-axis, there's symmetry. It looks exactly the same, or you have a mirror image on both sides of the y-axis. Therefore, this is an even function, which we saw algebraically because f of negative x equals to f of x. Next, we want to determine algebraically whether this function, 2x squared plus 3x minus 4, is an even function. So whenever we want to check algebraically, we need to know that f of negative x is equal to f of positive x. So we know what f of x is. F of x is the easy part. That's 2x squared plus 3x minus 4. F of x is given to us. We want to calculate what is f of negative x. So f of negative x, once again, this is your input. So each x in the expression is going to get replaced with the input. Okay, so f of negative x to the second power, once again, is x squared. Negative times a negative is a positive. Over here, however, 3 times negative x is a negative 3x because a positive times a negative is a negative. So we have 2x squared minus 3x minus 4. These are not the same because they're almost the same, but notice that this negative 3x, positive 3x are a little bit different. Therefore, this is not an even function. Okay, and if you were to graph this on a website like Desmos, I'm doing a very rough sketch. Here's what the function looks like. So with the y-axis, it's not symmetric because we don't have a mirror image on both sides of the y-axis. Therefore, this function is not even. Okay, now let's talk about odd functions. For odd functions, f of negative x has to equal to negative f of x. Graphically, here's what it looks like. So let me explain kind of what this is saying. So f of negative x, let's take any x value. Let's take x equals to 1. The output for x equals 1 is this point. So what this is saying is if we take f of negative x, so which means if we take f of negative 1, then this point, the output, actually becomes the negative of that, whatever that output is. Let's take another one. If x was 2, this is the corresponding output. So f of negative 2, that output has to be the same value, but the negative of that value, which would be down there, and so on and so forth. So this is called an odd function when f of negative x, which means the value of the negative input is going to be negative the value of the output. And graphically, a function is odd if it's symmetric with respect to the origin. So this is your origin 0, 0. Okay, if you have a mirror image, so the mirror image, it means if you have one side of the graph like this, the other side has to be the exact, imagine this graph being flipped over, so it's the mirror image on the other side. Here's an example of an odd function. If you look at the origin, which is here, we have a mirror image on both sides. Therefore, this is an odd function. Here's how we test it algebraically. F of negative x has to equal to negative f of x. So let's take an example. Determine algebraically whether the function f of x equals to negative 3x cubed plus 5 is an odd function. So algebraically, we want to determine is f of negative x equal to negative f of x. So we got to calculate both things, right? Because before we just had f of x, now we have negative f of x. So we're going to calculate both things. Let's start with f of negative x. For f of negative x, this becomes your input. So we have negative 3 times your input. So the x value in the expression gets replaced with the input. So that's going to be negative 3 times negative x to the third power plus 5. If I simplify that, remember order of operations, we got parentheses, exponents, then multiply, divide, then add, subtract. So the exponent has to be done first. We cannot multiply these. Negative x cubed is negative x times negative x times negative x. So this is a positive x times negative x is a negative x cubed. So this becomes a negative x cubed. I'm sorry, let me rewrite that. So negative x to the third power is actually a negative x cubed. I should put this in here. Now, once I do the exponent, now I have a negative times a negative. Now I can multiply this. This gives me a positive 3x cubed plus 5. Okay, so negative x to the third power is this negative x cubed. Then we have a negative times a negative, which is a positive 3. So we got 3x cubed plus 5 as f of negative x. Okay, positive 3x cubed plus 5. Now we got to figure out what is negative f of x. So negative f of x, it means that you take this whole entire expression, negative 3x cubed plus 5, and you just add a negative to the front. Okay, so negative f of x means we keep f of x the same. We keep that same expression, just add a negative to the front. So this is going to distribute, and negative f of x, we add a negative to the whole expression. This becomes a positive 3x cubed. Negative times a positive is a negative 5. So now we want to compare, does f of negative x in fact equal to negative f of x? And it doesn't, because we got a plus 5, we got a minus 5. So therefore, this is not an odd function. Okay, let's take another example. So for the next example, we have f of x equals negative 3x cubed plus 2x squared plus 5. We will do that in class. And then the next example we will also do in class. Now let's talk about local maxima and local minima. This is a formal definition. You can read it if you want to, but I'm going to simplify it for you guys. A local maximum is basically a turning point. Same with the local minimum. So these, to simplify, are turning points. Okay, so local maxima, local minimum, it means that around its neighbors, it's the lowest or the highest points. Okay, so if I look at this point, for example, it's a turning point for one. And around its neighbors, like immediately the x values that are immediately around this point, that's the lowest point, which is why it's called a local minimum. So locally around its neighbors, it is the lowest point. Same thing here. This is a turning point. A turning point is when the graph turns. The graph is going up, then it goes down. This one is a local maximum because around its neighbor, it is the highest point. This one is a local minimum. It turns. So any turning point is going to be a local minimum or a local maximum. Here the graph turns. So around its neighbors, this is the lowest point. So the local maximum is going to be the point 0.03. There are two local minimums. One is a point -2, -1, and the other one is point 1, 0. Okay, local maximum, turning point. It's the highest point around its neighbor, so it's a local maximum. This is a turning point, but around its neighbors, it's the lowest, so it's a local minimum. Same over here. 1, 0 is a turning point. Around its neighbors, it is a local minimum because it's the lowest point around its neighbors. Now, over which intervals is a function increasing? Increasing, once again, remember that when you're going left to right, if the function is going, if the y's are going up, that's increasing. So the function is increasing here, and the function is also increasing here. So on these two intervals, the function is increasing. The y values are going up. But when we ask for an interval, this is always referring to the x value. So we want to find out over which x value is the function going up. So that's between here, -2, and it goes up, goes up, goes up until it hits 0, and it kind of stops there. So the function is increasing between -2 and 0. And then same thing over here. The function starts increasing at x equals to 1, and then it goes up from there. And just keeps increasing. The arrow means it keeps increasing, so it's going to approach infinity. And we have to put a union because we have two disjoint sets where the function is increasing. Okay, next question, where is the function decreasing? Decreasing, it means when we're going from left to right, the function is going down. So the function is decreasing here, and the function is decreasing here. The y values are going down over these intervals. Okay, now what are these intervals? So the first one, this is -infinity. First interval, the x values are from -infinity all the way until 2. Until -2. And then it's also decreasing between 0 and 1. So over these intervals, the function is decreasing.